But the Mesozoic is this period of time at 250 million years, MYA, million years ago, 250 million years, about 65 million years ago. That was the Mesozoic. It means middle animals. And these are words you've heard. At least you've heard Jurassic. There's a new movie out, right? Triassic, Jurassic, Cretaceous. These are the periods. And amniotes started to diversify back here in the Permian. And we hit the Mesozoic, and this is the, well, we often call it the age of dinosaurs. So I'm going to define the word dinosaurs as we go along, or narrow our definition of it. That's kind of what we're talking about, the age of dinosaurs here. I want to introduce us to these ancient creatures, these ancient diapsids. So, dinosaurs first entered human consciousness in the 1830s and 40s. People first started to see these fossils and couldn't understand them. And we've always been fascinated by dinosaurs, particularly kids. Some of you will have kids one day, and your 4- and 5-year-old will know dinosaurs better than you do. And you'll have all these cool books that'll be accurate or not. So, there's just a fascination with these creatures that extends on into very elaborate worlds. Some create called Dinotopia, which is a series of books about an island in the Pacific where dinosaurs are still living. There's all sorts of bad movies that have dinosaurs in them. There's the original King Kong from the 30s, and Cowboys and Dinosaurs, awesome movie from the 60s. The Land Before Time. Just a heads up, anytime you see Doug McClure in a movie, you know it's really bad. The character in The Simpsons, Troy McClure, is modeled on Doug McClure. But anyway, so we've had dinosaurs around for a long time. Haven't always understood them. Some of the first dinosaurs discovered were in England in the 1830s and 40s and 50s. I'll introduce those people later. And these are what the Victorian people thought of dinosaurs, big, vicious lizards, essentially. Okay. We're still fascinated by them. Anyone been out to Cabazon, the big concrete dinosaurs right by the interstate there? Anyone that still watch Pee-wee's Big Adventure? Pee-wee's Big Adventure out there by the dinosaurs. It's a horrible movie with about 10 great scenes. So anyway, just drive along, and they're everywhere. As people, trying to tempt people to get off the highway and spend some money. So we're fascinated by these things, is my point that I'm trying to make here. And the last 10, 15 years has been a renewed interest in I say undergraduate education on dinosaurs. And I forgot to bring these in. These are a couple textbooks on dinosaur biology. And we've been thinking about doing a class like this here. And this is actually a non-majors text where they use dinosaurs as the main subject to teach ecology and evolution and conservation and important ideas like that to non-majors. So lots of interest. So dinosaurs are a Mesozoic thing. That's why we're calling them Mesozoic, was really cool. And huge radiation of them and new discoveries all the time, new interpretations of old discoveries. There are also lots of other amniotes in the Mesozoic and other creatures in the Mesozoic, and we'll touch upon some of these along the way, but there are a lot of things back there that aren't necessarily dinosaurs. So let's define that. Dinosaur. What are we talking about when we talk about dinosaur? The word we've had for about 150 years now. Well, what are we talking about? And we've used words in this class in the strict sense, and I say go with a capital letter in the front of it, or in the informal sense, small a. Like, and it's the same with dinosaurs. We have small d dinosaur, and that is typically used to describe any large reptilian-like creature from the Mesozoic would be called a dinosaur in a non-strict sense. Small d. You probably had a bag of plastic dinosaurs as a kid, and probably some of the things in that bag are not dinosaurs. There's also dinosaur in the evolutionary sense, and that's how we're going to start using the word. And again, evolutionary sense means there's an ancestor, and then all the descendants. So there is a taxonomic category, Dinosauria. It's like I'm not sure what rank it gets these days, subclass, probably infraclass, something like that. But that means there is a described, recognized, monophyletic taxon, Dinosauria. And, any monophyletic taxon has the ancestor and all the diversity that comes off that. That's how I want to use the word dinosaur from here on out. So these are dinosaurs, members of that crowd Dinosauria, capital D with the A-I-I-A on the end. These are not dinosaurs, but I'll bet they were in your bag of plastic dinosaurs. They're not a member of that group. These are dinosaurs, but these are not. They're ancient Mesozoic creatures, but they're not dinosaurs. We'll talk about them because they're fun. This is a dinosaur. This is a member of the Dinosauria. So we've been saying for 25 years now, dinosaurs didn't go extinct. This one small branch of them squeaked through that extinction event, and they gave us birds. So, Mesozoic creatures. Just an example here, and I've used this before. This is Dimetrodon, and in all the books on children's books on dinosaurs, there's Dimetrodon in there, and he's in your bag of plastic dinosaurs almost always. Very, very distinctive creature, but he's not a dinosaur. He's not even a diapsid. This is a synapsid animal. This is a mammal relative. So we want to be careful when we use these words. So there's an evolutionary tree. And have a look at this. There's the synapsid, the mammals here. Squamates, there's the lizards, lepidosaurs, right? There's birds. And then here's the dinosaurs, right in here. There's the flying ones. They're actually not dinosaurs. There's the crocodilians and the turtles. And the swimming ones are down here. They're not dinosaurs. So that's a highly simplified evolutionary tree there. And we want to play with all these extinct ones in the next couple of days because they're all worth looking at. So, really what we're talking about when we talk about these Mesozoic creatures we want to talk about is ancient amniotes. The Mesozoic amniotes is what I want to focus on, more or less. So, Mesozoic, again, really, really cool. Instead of calling it the age of dinosaurs, we'll call it the age of amniotes from here on out. Okay, did that. So a little bit of background to get a set where we're headed. There's our time scale again. We've used this before, but let's look at it again. There's our three periods: Paleozoic, Mesozoic, Cenozoic, and we're spending pretty much all our time in here now. We'll bleed into the Permian a little bit, but mostly we're playing in the Mesozoic here. Mesozoic is the Triassic, Jurassic, Cretaceous. And unlike studying modern creatures today, we've got to keep in mind that when we look at these Mesozoic creatures, they have an evolutionary span of time. They exist in time and through time. But if you're doing a study on Channel Islands foxes, you're looking at one slice in time on our planet. But when we're looking at these ancient things, we often have millions of years to play with. So yeah, there's the time scale of Triceratops, many millions of years. There's Channel Islands foxes, if that's your study there. So it's a very different way to approach biology, I think. So this would be time scale of something modern. We call this ecological time. The time we measure in sometimes just months, sometimes centuries, but very small slices of time. That's ecological time. And that's how we study things generally. But when we're studying, I didn't have a picture there. When we're studying ancient things, we often have to think, yeah, they had ecology. But we also have tremendous spans of time. I have no idea how that guy got that picture of that gal. Look at that. Up there with that cool leopard. Maybe it's Photoshop, I don't know. The other thing we lose track of sometimes is dinosaurs aren't just mounted bones in museums. They didn't live in isolation. You didn't have T-Rex walking around Montana. They lived in communities and ecosystems, just like living things do today. And so we can study the Channel Islands fox or whatever and understand how ecological relations work, and we can apply those to any evidence we get of these ancient things. These ancient things did have ecology. And sometimes that ecology, sometimes there's clues to it in the fossils that come down to us. They had food chains, for just one example. We got many, many, many. There were clearly food chains back there. We had no reason to assume the Mesozoic world worked differently than ours. So there were the producers, and there were the herbivores, and there were the carnivores, just like there are today. We often don't have all the pieces because the fossil record is incredibly incomplete. But when we get different pieces, we can put them together. It's called paleoecology. All right, just a bit on time scales. We keep touching on this. Let's just touch on it one more time. Yeah. So, you often see these evolutionary trees, and they're layered over the time. And then that you read them, you know, this particular thing, well, the fossils go back at least this far, and they go at least this far. And time scale usually on the vertical axis, or sometimes it's on the horizontal axis. Here's a scale for the history of Earth, and it's about 4.5 to 5 billion years old. That's the span of the history of our Earth. And all the stuff in brown here, well, that's a long time ago. We don't know a lot about that because that's a very long time ago. Any geologic formations or fossils that developed back here, they've had a long time to be buried or destroyed. So that highly speculative back there. About 600 million years ago, we start getting good fossils, and that's not so far back that a lot of them are still with us. So this is the part of our Earth's history we know most about 10% of the total. Life goes back about this far. We know very little direct evidence back there, but starting about 600 or 700 million years ago, we start to get decent fossils. And so this is the part of the scale that we know most about. It's where we spend most of our time. Just the past 500-600 million years, 500 million years, we're around. Yeah. So we take this whole span of Earth's history, and we focus on that 10% because, you know, I come back to this again and again. The closer we are to us, the thicker the chapters are in the book, and it's the same kind of thing here. The more recent, the more we're interested, the more we know. And so you can see, here's what 2 billion years, one block of time there. Here's 600 million years, and we got all these different little segments to them we know a lot more about. So there we go. Last 500 or so, 70 million years. And here's just another way to look at it again. Paleozoic, Mesozoic, Cenozoic. 3 eras, and then broken up into periods. And we did this. The Paleozoic we often call the age of fishes. About 500 million to 225 million years ago. This is when vertebrates first originated and diversified in water, and towards the end of the Paleozoic, they started coming up on land. We get those primitive tetrapods. And that's the Paleozoic. We already covered that. And, you know, the Mesozoic was cool. The Paleozoic was awesome, too. Mesozoic is often called the age of reptiles, the age of dinosaurs. There's our dates on it, 225 million years ago, about 65 million years ago. These major eras are usually punctuated by some huge event, like an extinction event. You know, these aren't just random, oh, it started here. Something happened 65 million years ago. We say, okay, it's the end of the Mesozoic. And there it is there. We just did this. Triassic, Cretaceous. And this, again, is what Victorian people in England thought dinosaurs looked like. They always were biting each other. And then the Cenozoic, 66 million years ago to the present time, that is the age of mammals. And some people are advocating we start a new era now, the Anthropozoic, the human time. And it's not a compliment to us, it's just we're doing so much damage that we're changing things. Okay. That's the introduction. Any questions? Let's push on. Well, I have to say that change. slideshow again. How do we study this stuff? A little bit of background on geology and paleontology. First off, I think this is obvious, and you're probably aware of this, but when we look at these, when you look at a layer of geologic strata, you dig something out of a mountainside, there are layers in that, and again, they're named. These are the names we just did: Triassic, Jurassic, Cretaceous. But more than just the names, for time, there are layers in the Earth's crust that were laid down in these different times. And so you can dig down and find Jurassic layers, and they're called strata, that's Latin for layer. And unless they've been disturbed, the older ones are deeper down. Just like in an archaeological site, if you go to an archaeological site, a Native American site or whatever, you see the most recent habitations at the top, and as you go down, it's like turning pages in a book, you find older and older layers. And so where there's fossils, the older ones are farther down, unless they've been disturbed. And so when you take a geology class, anyone had geology? Yeah, so you drive around and look for this kind of stuff, right? Yeah, there's those layers. And someone like Chris Wheeler can look at those and very quickly interpret them for you. It's like reading a book. And look at that cool picture. Someone once joked, a geologist, that geology is the study of rocks at road cuts, because that's where you see them so beautifully exposed. And here's an example of layers that were certainly laid down horizontally, but geologic events have pushed these in, and now they're vertically oriented. You can see some of them have been folded and broken here. That's what I mean by disturbed. When they're not disturbed, it's like this. But you have, like anything, you have to know what you're seeing. This is a site that we used to go to when I lived in Ohio near Cincinnati, and this is an ancient ocean bottom all along here. Look at these rocks here, these broken out rocks here. You go out there and you park very dangerously on the side of the state highway, and you walk up there, and this is what you find. Just all over the ground there. These are Ordovician era Paleozoic ocean fossils. These are brachiopods and crinoids. Brachiopods, that looks like a clam, but it's not. That's a type of echinoderm. And we would occasionally find trilobites in these things. But that, southern Ohio, bottom of an ancient ocean. So there's a geologist, and he's putting his finger right on the layer. This was the top of the habitat as we transitioned from Permian to Triassic. This is Mesozoic dirt up here, Paleozoic dirt down here. So in these layers, there are often fossils preserved. Different types of layers preserve fossils better than others. We often see fossils. So fossils come in all sorts of different way and manifestations. Vertebrates often leave bones as fossils. Those are the most informative. But fossils come in other forms as well. Rarer types of fossil could be skin impressions, like this dinosaur skin here. Sometimes eggs are fossilized, and we've talked about fossil eggs earlier. Now, those could be very informative to get you an idea of the biology of the creature. There's fossil footprints of some ancient Mesozoic creature. And again, there's been a shift in the geology. They're now on a vertical rock face. That is interpreted as a fossil burrow. Some creature, and that is a burrow as its home, and filled up and fossilized. Dr. Wheeler has a whole drawer full of Mesozoic poop. It's called a coprolite. That's Mesozoic feces. So, lots of clues. And there's a basic process to fossilization, and I kind of summarized it here. There's discovery, there's the creature. And so it goes through a series of stages, and all these things have to happen just right in order for us to get the fossil. And if at any one point in time it changes or something doesn't happen, we don't get the fossil. And of course, the last one might be fossil. There's gazillions of fossils we will never see because they're buried in places that will never be exposed. But if all these things happen, And we're really lucky we get that fossil. So it starts with someone dying. Or leaving a footprint, I suppose, or pooping. And the problem with a vertebrate in particular dying, or any animal, so is there's lots of things that eat dead animals. And so fossils, or an animal, when it dies, often quickly gets dispersed. And if that happens, we might find fossil bones, but we don't get an articulated skeleton. Best kind of fossils happen when the animal's buried quickly. And that often happens in aquatic habitats where it sinks into the ooze and is covered up or buried in a sandbar very quickly, and it's able to escape that kind of destruction. So right off the bat, we have to have a proper death. So this is a series of bones. These are little pterosaurs, little flying Mesozoic reptiles, big wings there. And this may have been under a roost where they lived for years and years and years. When they died, they fell down here and they were scavenged and picked apart. And we just have a bunch of bones there, all mixed up, probably from different periods of time. That's useful, but not as useful as something like that, where that little guy died, for whatever reason, got buried quickly, and we ended up with a largely articulated skeleton. So, there's that beginning part there. We have to get the death, we have to get the burial, preservation started. Flesh rots away, and the bones are left. What happens to the bones, if they're in the right conditions, and they're not always, if they're in the proper conditions, the bones will get mineralized. When you see a fossil bone, it's made of rock. It's made of minerals. It's not the original bone. The original bone's gone. What's left is the bone tissue's been replaced by minerals. And the right conditions have to be there. The right levels of moisture and minerals in the soil in order for that to happen. Silica, iron, and lime compounds, these are immobilized by water. And in the right conditions, they will replace the calcium salts and the phosphorus salts in the bone. And you can end up with beautiful replica. But if conditions aren't right, you don't get that. And this came up to me just recently. I was reading an article about the Titanic, the big ship that sank in 1912, and they went out and they recovered many bodies floating in the ocean after that, and they were brought back to Canada, and those that weren't claimed were buried. And so there's a grave somewhere in Newfoundland, Canada, I believe, where the Titanic victims are buried. And nowadays they say, let's try to identify this person. They dig down, take a bone out, look for DNA, and see if they can, because a lot of them are just unnamed, and there's a whole row of children that were buried without names. And they dug down into some of these child's graves to get a sample of bone, and they found nothing. Nothing. The nails from the coffin. And the coffin is rotted away, and the bones are completely dissolved. So that's what happens more often than not. You don't get anything. This is a dinosaur bone, sectioned in a microscope. You looked at bones a couple weeks ago in lab, right? Or was it last week's just that? Look at the detail there. Does that look like the bone section you looked at? Does that look like the bone you looked at? That's a bird bone there. So some of this preservation can be remarkably detailed. So here's our phase there. And it takes a long time for this to happen, for the time and water and minerals there. And then, like I said, if we're really lucky, it erodes out and somebody finds it. And then we get the good of the fossils. A little bit about geology. Again, from the time scan, the oldest stuff is further down. We always know relative dates. If sediments haven't been disturbed, we always know this is older than this, unless things have been disturbed. That's called relative dating. You're older than that. But can we put an actual number on that? Can we say 112 million years ago? We can say, this is older than that, but when we say one of them, put an actual number on that. And it turns out there are ways we can date rocks. We can put an actual number on that. And it has to do with radiometric dating. It has to do with when a particular mineral is formed locked in it is a certain amount of a radioactive material. And that radioactive material breaks down through time. And so if we can estimate how much was originally there when it was formed, and there's ways to do that, and then you look at how much is there now, and you know how fast it decays, you can say, okay, this rock has been decaying, this mineral has been decaying for X millions of years. And carbon dating is done for much more recent things. These other isotopes, these other radioactive things are done for older things. And so we can get pretty good dates on certain kinds of rocks. Turns out radiometric dating works best with igneous rocks. Remember your geology? If you didn't take geology, you probably took it in junior high or had a science class. Igneous rocks, these are volcanic rocks. So volcanic layers we can date better than other types of layers. For example, sedimentary rocks. Remember the other kind of rocks, like on the bottom of an ocean or in a desert where the sediments get compressed into rock? Sedimentary rocks are not as easily dated radiometrically, not as accurately. So we can sometimes date this layer, but not that layer. We can date this layer, and then we know this layer is a little bit newer, but sometimes we can date this layer, and we can date this layer, and then we know this one's in between. So we can bracket things and get a pretty good idea of the dates of a lot of these strata. Unfortunately, just the way biology works, geology in this case, the best fossil-bearing rocks are sedimentary rocks, the ones we can't date. And it's very rare to find fossils in igneous rocks, the ones we can date. So you end up doing a lot of this. And geologists have been doing this for 100 years, so they're pretty good at it. Anyway, let's look at the Mesozoic real quickly, some of the major events that were happening there, the major periods there. Did that, yeah. So Triassic, Jurassic, Cretaceous. Let's just make that part of our vocabulary. You know, a good exam question is not, when did the Jurassic start? I'm not good with numbers. I don't expect you to be good with them either. So Triassic, Jurassic, Cretaceous. The Mesozoic starts with a big extinction event. The Permian-Triassic transition, the Paleozoic, Mesozoic transition, there was a huge extinction event there. One of several that we've had in our history's planet. And so late Permian, the fossil beds are full of life, and early Triassic, we had a big die-off. Off the top of my head, I don't remember what the hypothesis for that event was. It was a climate change event. Yeah, that was a climate change event involving volcanism in Siberia. Had an enormous period, enormous period of volcanism, and it's now Siberia. A lot of garbage in the atmosphere cooled the planet off, and the planet became cooler and drier. So Triassic, 250, 200 million years ago. And this is where we start seeing the first dinosaurs, which we'll get to maybe later today. And look at this, though. We're not even near here yet. Mammals go all the way back to the Triassic. They were just pretty insignificant through most of the Mesozoic. I think these are cool, so I put them in here. These are these maps of the continental positions at different points in time, and that's what it's thought that the Triassic looked like. You can see, you can kind of get an idea here. Here's North America, South America, and this is Antarctica and Africa in here. Triassic, it means three layers. I'm not sure what ASIC means, but it's trying 3 layers, and there's 3 very distinct layers of strata in the Triassic, and I'm not worried about that detail, but that's what the word means. So it was a hot and dry, a more arid climate than we had previously. I think I said a minute ago it was cooler, it was arid and dry. Kind of a continuation of the Permian. And this is where the first dinosaurs show up. Transitioning into the Jurassic. There's the Earth in the Jurassic. Map up there again. Some of the continents are vaguely recognizable. The South American coast, North America there. A little bit more recognizable there, but still pretty different than what we think of today. Anyway, the Jurassic is a period of a flowering of dinosaur diversity, and most of the major big dinosaur finds, early on at least, were Jurassic. In Colorado, we have Dinosaur National Monument, which is dedicated to a really rich fossil bed of this era. The big classic dinosaurs are Jurassic animals, and it's no accident they made a book and a movie about it. Climate moderated, forests reappeared. Not really the rainforests or the Carboniferous, but there was a more moderate climate. The Cretaceous follows on. Dinosaurs diversified, and then we come to our end point. Cretaceous, the root there is chalk, and these great layers of chalk, like these are the White Cliffs of Dover on the south coast of Britain. These are Cretaceous formations, and these are ocean bottom formations. The chalk comes from the seashells of gazillions and gazillions and gazillions of ancient sea creatures that got compressed into rock here, kind of soft, flaky rock. We had huge ocean expanses, coastal oceans, broad oceans. That's the Cretaceous, and it's starting to look a little bit more like home. And look at North America. And this shows up today, this difference, and I'm a freshwater fish biologist, and in the eastern part of North America, east of the Rockies, and on the west coast, we have two different fish faunas. The western fishes are more Asian in their relationships, the eastern fishes are more European in their relationships, and it goes back to this big ocean separating them a while back. So this is a time of shallow oceans and a lot of sea life. The Cretaceous ends with the extinction of dinosaurs. Different hypotheses about why that happened. The one that's currently in vogue is it was a meteor strike or a comet strike. It was now Yucatan and the ocean, and threw so much debris in the atmosphere that the sun was choked out for maybe tens of thousands of years, and large creatures disappeared. So anyway, this is the geologic profile for Western North America, and all these named and layers tracked for 150 years now. People have been drawing maps like this. This happens to be the Grand Canyon. There's the Colorado River down here. Colorado River has spent the last, I don't know how many millions of years, carving through this stuff. And if you are knowledgeable, you can stand in the Grand Canyon and see these different layers, and you can see, gosh, I'm looking at Cambrian rocks that are 600 million years old. There is that Western North America. There's 260 million years of history there, back to the Permian. That's about 2,000 meters, 2 kilometers of Earth's crust there. And that's about 2,000 meters. So you walk from here, you can picture we're on campus, right? If you walk from here to here, that's the amount of Earth's crust that's been laid down since the Permian. I think that's kind of cool. Okay. All right, let's take a few minutes here. That's a good spot. Put your pencils down for a few minutes, and we'll pick up again around 10. I'm going to go grab something from my office. I've been putting off. I know I promised we moved to that other room. The other room isn't air conditioned, and I'm deciding that even though I don't like this room, it's kind of hot over there as you get towards noon. But I think we'll just stay here. Let's see, I gotta go grab your exams.
Do that. I do, Lord.